Have you ever wondered how computers learn to see, speak, and even create? The answer lies in the fascinating world of machine learning, and at the heart of many of its most incredible advancements is a powerful tool, PyTorch. Before we get started, a quick note. All of the code examples for this course are hosted on our GitHub repository. Just click the link in the description of this video to access everything. Feel free to clone, explore, and follow along as we go. In this complete tutorial, we'll take you on a journey from a complete beginner to a confident PyTorch practitioner. But first, why PyTorch? What makes it the framework of choice for so many researchers, developers, and AI giants? The beauty of PyTorch lies in its simplicity and Python-first approach. If you're familiar with Python, you'll feel right at home. It's intuitive, easy to learn, and allows for rapid experimentation. This means you can spend more time bringing your ideas to life and less time wrestling with complex code. One of PyTorch's most celebrated features is its dynamic computational graph. Imagine building your machine learning models on the fly, with the flexibility to change and adapt them as you go. This define by run philosophy is a game changer for researchers and anyone pushing the boundaries of what's possible in AI. It makes debugging a breeze and empowers you to create complex and innovative neural networks with ease. But PyTorch isn't just for research. It's a production-ready framework with a robust ecosystem of tools and libraries that streamline the process of deploying models in real-world applications. From natural language processing that powers a new generation of chatbots to computer vision that enables self-driving cars, PyTorch is at the forefront of AI innovation. By learning PyTorch, you're not just learning a framework, you're unlocking the potential to build the future. You're joining a vibrant and growing community of developers and researchers who are solving some of the world's most challenging problems. So, if you're ready to dive into the world of deep learning and build intelligent systems that can learn and reason, you're in the right place. Get ready to master PyTorch and let's start building the future together. Welcome back. In this first practical step, we'll do the most fundamental thing you need to do in any PyTorch project: import the library itself. On the screen, you can see the essential line of code. It's as simple as it gets in Python. Import torch. We import the library and give it the alias torch. This is a universal convention in the PyTorch community. You'll see torch used in virtually every tutorial, research paper, and open source project. Sticking to this standard makes your code instantly recognizable and easier for others to understand. Now, before we dive into creating tensors or building models, there's a small but crucial best practice I want you to adopt: checking your PyTorch version. Why is this important? Well, the world of AI moves fast. PyTorch is constantly being updated with new features, performance improvements, and bug fixes. Knowing your version helps you debug issues, look up the correct documentation, and ensure that if you share your code with someone else, they can create the same environment to get the same results. You can easily do this by printing the version attribute. When you run this, you'll see an output telling you the exact version you have installed. With that one import statement, we now have the full power of the PyTorch library at our fingertips. In the next section, we'll start using it to create the core data structure of PyTorch, tensors. Alright, let's talk about the single most important concept in PyTorch, the tensor. The name might sound a bit intimidating, but the idea is actually very simple. A tensor is just a container for numbers, a way to organize data. In fact, all the data you'll ever feed into a neural network and all the internal parameters of the network itself will be stored in tensors. So let's build up the intuition, starting from the ground up. At the most basic level, we have a scalar. You can see on the slide this is called a zero-dimensional tensor. Don't worry about the dimension part yet. Just think of it as a single number. For example, the number 5. That's a scalar. Now, what if we have a list of numbers? Maybe the prices of three different items in a shopping cart. That's a vector, which is a one-dimensional tensor. It's just a sequence of numbers in a single row. Okay? Let's take it one step further. Imagine arranging numbers in a grid with rows and columns, just like a spreadsheet or a tic-tac-toe board. This is a matrix or a two-dimensional tensor. A black and white image is a great example of a matrix where each number represents the brightness of a pixel. So, tensor is really the umbrella term that covers all of these. A scalar is a tensor, a vector is a tensor, and a matrix is a tensor. The real power comes from the fact that tensors can handle even more dimensions. A color image is often a 3D tensor with dimensions for height, width, and color information. A video could be a 4D tensor. So, to put it simply, tensors are the language of data for PyTorch. By understanding this simple hierarchy from scalars to vectors to matrices and beyond, you've already grasped the core concept you'll use throughout your entire deep learning journey. Here, we are going to unravel the mystery behind tensors and learn how to build them from the ground up. By the end of this, you'll see that they're just simple building blocks for all the amazing things we can do in deep learning. Let's get started. All right. Let's start with the simplest building block, the scalar. Think of a scalar as just a single, lonely number. It has 0 dimensions. In our code, we've created a tensor holding the number 42. When we ask for its dimensions, PyTorch says 0, and if we want the actual Python number back, we use the dot-item method. Easy peasy. It's the atom of our data universe. Next up, the vector. Now that we have our atom, let's build a molecule. If a scalar is a single number, a vector is a list of numbers, all in a single row. It has one dimension. Here, our vector holds the numbers 2 and 3. You can see it has one dimension, and its shape tells us it has a length of 2. It's like a single list of your favorite things, or coordinates on a map. Now things are getting interesting with the matrix. A matrix is a grid of numbers with rows and columns, just like a spreadsheet or a tic-tac-toe board. It has 2 dimensions. Our matrix here is a 3 by 3 grid. PyTorch confirms it has 2 dimensions, and its shape is 3, 3, meaning 3 rows and 3 columns. This is a crucial step up, as 2D tensors are the standard way we represent things like grayscale images, where each number is a pixel's brightness. Finally, let's enter the third dimension with a 3D tensor. Imagine taking a bunch of those matrices we just made and stacking them on top of each other. That's a 3D tensor. It has 3 dimensions. Our example here has a shape of 1, 2, 2. You can read that as I have one matrix, and each matrix has 2 rows and 2 columns. These are perfect for more complex data. For example, a color image is often a 3D tensor with 3 2D matrices for the red, green, and blue color channels. They're also great for sequences, like a series of measurements over time. So, to wrap it all up, the main difference between all these tensors is simply the number of dimensions they have. A scalar is a point, a vector is a line, a matrix is a flat square, and a 3D tensor is a cube. Each one adds a new dimension, allowing us to represent more and more complex data. As you get into more advanced deep learning, you'll use tensors with even more dimensions, but they all build from these simple fundamental ideas. Now that we know how to create basic tensors by hand, let's dive into the PyTorch playground and learn some powerful functions that let us create common types of tensors automatically. These are the tools you'll be using every day. Random tensors. First up is the torch.rand function. This is your go-to for creating tensors filled with random numbers between 0 and 1. It's incredibly useful for initializing the weights in a neural network, giving it a random starting point to begin learning. You'll notice the torch.manualSeed42 line. That's our little magic trick to ensure that every time we run this code, we get the exact same random numbers. This is critical for making our experiments reproducible, so if we find a great result, we can get it again, zeros and ones. Sometimes you don't want random numbers. You just need a tensor of a specific shape filled with a default value. That's where torch.zeros and torch.ones come in. They are perfect for creating placeholder tensors that you'll fill with data later, or for creating masks to hide or show parts of another tensor. Here we've made a ghost grid of zeros and a cloud array of ones. Simple, clean, and very useful for a wide variety of tasks. A range of numbers. What if you need a sequence of numbers, like a timeline or a set of indices? Torch arange is your friend. It works just like Python's built-in range function. You give it a start, an end, and a step, and it creates a 1D tensor or vector with those values. Our step ladder starts at 5, goes up by 3, and stops before it reaches 15. It's a quick and easy way to generate predictable sequences without having to type them all out by hand, creating tensors like others. Finally, one of the most convenient tricks in the book, the like functions. Let's say you have a tensor and you need another one with the exact same shape and data type, but filled with zeros. Instead of manually checking the shape and type and then passing them to torch zeros, you can just use torch zeros like. It's like using a cookie cutter. It takes all the properties from your input tensor and creates a new one based on that template. It's clean, efficient, and helps you write less error-prone code. There are other versions too, like ones-like and rand-like, and that's a wrap on our tensor creation playground. With these functions, you're now equipped to create all kinds of tensors for your future projects. In our journey with PyTorch, we've learned how to create tensors. Now, we're going to zoom in on a critical detail, the data type or dtype. Think of dtypes as different materials you can build your tensors from. Some are heavy and precise, others are light and fast. Choosing the right one is key to building efficient and effective models. Let's explore the toolbox. Floating point types, the standard. First up, we have the floating point types, which are used for numbers with decimal points. The absolute champion and default type in PyTorch is torch.float32. It gives you a fantastic balance of precision and performance, making it the standard for training nearly all neural networks. But what if you're a scientist running a high-stakes physics simulation where the tiniest rounding error could throw off your results? That's when you bring out the heavyweight, torch.float64 or double precision. It's twice as big and much slower, but it gives you incredible precision. For most deep learning, it's overkill, but for scientific computing, it can be essential. Floating point types, the speedsters. Now, let's talk about speed. In the world of massive models, Float32 can be slow and memory hungry. This is where the 16-bit floats come in. Torch.float16 cuts memory usage in half, which can dramatically speed up training on modern GPUs. The trade-off is a much smaller numerical range, which can sometimes cause issues. To solve that, Google introduced torch.bfloat16. It maintains the same large range as Float32 while still using only 16 bits by sacrificing some decimal precision. This makes it much more stable for training, and it's quickly becoming the new favorite for high-performance computing on TPUs and the latest GPUs. Integer types, the counters. Next, we have integers, whole numbers. The most common one you'll see is torch.uint8, the unsigned 8-bit integer. It holds values from 0 to 255. Why is that range important? It's the standard for representing pixel intensities in digital images. So whenever you load an image, it's likely coming in as a uint8 tensor. For other tasks, like representing categories, labels, or indices, we use signed integers like torchint64. If you have 10 classes in a classification problem, their labels will be stored as integers, typically in a int64 tensor, specialized types. The specialist. PyTorch also has specialists for specific jobs. The torch.bool type is incredibly simple. It's just true or false. Its main job is to create masks. You can perform a comparison, like asking which values are positive to get a Boolean tensor, and then use that mask to filter, select, or modify data. It's a fundamental technique for data manipulation. And for our friends in engineering and physics, we have complex number types like torch.complex64. These are essential for any work involving signal processing, like audio analysis with Fourier transforms, or simulations in quantum physics, quantized types, the optimizers. Finally, we have one of the coolest tricks for model deployment, quantization. After you've trained your big, powerful Float32 model, you often need to run it on a less powerful device, like a smartphone. Quantized types, like torch.kint8, allow you to convert your model's weights into highly efficient 8-bit integers. This process makes the model drastically smaller and faster for inference, usually with only a tiny acceptable drop in accuracy. It's the key to getting your models out of the lab and into the real world. Alright, so far we've learned how to create tensors with different shapes and data types. Now let's look at 3 incredibly important arguments you can set when creating a tensor: device, dtype, and requires grad. These are what give you fine-grained control and unlock the full power of PyTorch. First, we have this line, device equals torch dot. Device open parenthesis CUDA:0 if torch.CUDA dot is available, else CPU close parenthesis. This is a standard and very important piece of code. It checks if your computer has a compatible NVIDIA GPU which uses CUDA. If it does, it sets the device to CUDA. If not, it defaults to the CPU. When we create our tensor, we pass in this device variable. This tells PyTorch, I want this tensor to live and perform its calculations on the fastest hardware available. Moving tensors to the GPU is the key to accelerating deep learning training. Next, we have dtype equals torch.bfloat16. We're being very specific here. As we learned in our dtypes tutorial, bfloat16 is a modern, memory-efficient format that's great for training large models on the latest hardware. By setting this explicitly, we are making a conscious choice to optimize for performance and memory usage. Finally, and this is perhaps the most magical part of PyTorch, we have requires grad equals true. This is the switch that turns on PyTorch's automatic differentiation engine called AutoGrad for this specific tensor. By setting this to true, we're telling PyTorch, keep an eye on this tensor. I want you to track every operation it's involved in, because later I'm going to need to calculate the gradient with respect to it. This is the absolute foundation of how neural networks learn. It allows PyTorch to automatically figure out how to adjust this tensor's values to improve the model's performance during backpropagation. So, to sum it up, with these 3 arguments, we're not just creating a simple array of numbers. We are creating a sophisticated computational object, placing it on the optimal hardware for speed, defining its numerical precision for efficiency, and enabling it to be automatically updated as part of a learning process. This is what makes PyTorch so powerful. We're going to take a tour of the basic arithmetic you can perform on PyTorch tensors. It's easier and more intuitive than you might think. Let's start with our headliner act. A tensor we'll call galaxy scores. It's just a simple 1D tensor holding a few numbers. Now, what happens if we want to give every score a boost? We can just take our tensor and add a number to it, like galaxy on scores plus 5. PyTorch is smart enough to perform this operation on every single element in the tensor, creating a brand new tensor with the uplifted scores. The same thing works for multiplication. If we want to hit the warp drive and multiply all our scores by 3, we just use the star operator. Again, this creates a new tensor, warp or multiplied, with the results. But here's a key point and a common source of confusion. Notice that our original galaxy scores tensor hasn't changed at all. The operations we just did created new tensors. The original data remains untouched unless we explicitly tell PyTorch to change it. So how do we do that? Through reassignment. If we want to apply an alien tax and subtract 2 from our scores, we can do the calculation and then assign the result right back to the galaxy charn scores variable. Now, the original tensor variable points to this new updated data. Let's do it again with a star bonus of plus 10. See, the scores are updated in place. While using simple operators like plus and star is common, PyTorch also provides equivalent functions like torch.multiply. This does the exact same thing as the star operator, but can sometimes make the code's intent a bit clearer. Finally, the real power comes from element-wise operations between two tensors of the same shape. For example, if we want to square every score, we can just multiply the galaxy scores tensor by itself. PyTorch will match up each element and multiply it with its corresponding partner in the other tensor. And that's it. You now know the basics of tensor arithmetic in PyTorch. You can add, subtract, multiply, and perform powerful element-wise operations with a syntax that's clean, simple, and easy to read. And that brings us to the end of the first part of our PyTorch journey. Let's quickly recap everything we've accomplished. We started from the very beginning, understanding what a tensor is and how to create them, from simple scalars and vectors all the way to multidimensional tensors. We explored the tensor creation playground, learning powerful functions like rand, zeros, and arange. We then took a deep dive into the all-important concept of data types, or dtypes, learning how to choose the right tool for the right job, whether it's the standard float 32, the speedy bfloat 16, or the efficient int8 for quantization. Finally, we put it all together, learning how to perform basic arithmetic and, most importantly, how to control our tensors with device, dtype, and the magic of requires grad. You now have a rock-solid foundation in the fundamental building blocks of PyTorch. With these skills, you are more than ready for what comes next. In the second part of this series, we're going to take these fundamentals and start building. We'll look at more advanced operations, explore how to build our very first neural network, and really start to unlock the power of deep learning. I can't wait to share it with you, and it will be coming very soon. If you found this tutorial helpful and you're excited for part 2, please consider supporting the channel. Go ahead and hit that like button, subscribe so you don't miss the next video, and make sure to ring that notification bell to be the first to know when it drops. Thank you so much for learning with me today. Keep experimenting, stay curious, and I'll see you in the next one.